Here's a series of questions about electron configuration. The first reads, give the complete electron configuration of the following atoms or ions. First we look at the fluorine atom. So here's our periodic table, and here's fluorine. Remember to write the electron configuration. We'll start at hydrogen, and we'll walk our way across the periodic table. To get to fluorine, you first walk through the 1s orbital, then the 2s, and then most of the 2p. That's going to give a fluorine atom an electron configuration of 1s2, 2s2, 2p5. 2 electrons in the 1s, 2 in the 2s, 5 in the 2p. If fluorine were to become an ion and gain an electron, it's going to put that additional electron in the 2p orbital. We know that because the 2p orbital can hold up to 6 electrons, and previously it only had 5. So the fluorine ion will be 1s2, 2s2, 2p6. For iron, let's go back to the periodic table. Here's iron on the periodic table. To get to iron, we're going to begin filling orbitals from the lowest energy level first. Fill the 1s, then the 2s, the 2p, the 3s, the 3p, the 4s, and begin filling the 3d. Recall that the d orbital is in fact one energy level behind the valence electrons, or behind the s and the p orbitals. So the electron configuration of iron would look like 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6. When we get to larger atoms, we want to use a noble gas shortcut to save us a little bit of writing. Consider silicon. Consider silicon. Here's silicon on the periodic table. We can use the previous noble gas, neon, as a starting point and say that silicon is the same electron configuration as neon plus some additional electrons. Specifically, 2 electrons in the 3s and 2 electrons in the 3p. So silicon would look like neon plus 2 electrons in the 3s and 2 electrons in the 3p. Palladium is our next element. Palladium is a transition metal right here on the periodic table. It's quite large, so to save us some time, we'll say that palladium looks like krypton, or has the core electrons the same as a krypton, plus some electrons in the 5s and some electrons in the 4d. Specifically 1, 2, 3, 4, 5, 6, 7, 8 electrons in the 4d. So palladium would look like krypton, those 2 5s electrons, and 8 4d electrons. Let's do the same with calcium and bromine. Here's calcium. So calcium typically looks like an argon atom plus 2 additional electrons. However, the calcium we were concerned with had a +2 charge, meaning it's lost 2 electrons, and now is the same electron configuration as argon. It's not argon, it just has the same electron configuration as an argon atom. Here's bromine, which typically has the electron configuration of krypton with just 1 fewer electron in that 4p orbital. However, because our bromine has a -1 charge, it's gained an electron and now has the electron configuration of a krypton atom. Finally, we can use arrows to denote the electron spin of different orbitals, or electrons in different orbitals. Oxygen has the electron configuration of 1s2, 2s2, 2p4. Writing out those orbitals, I get something like this, where the 1s orbital has 1 suborbital, 2s orbital has 1 suborbital, the 2p has 3 suborbitals. Those 1s and 2s orbitals are completely full. the 2p has 4 electrons. Start by spacing out your electrons, have them all spinning the same way, then go back and fill your previous orbitals. Here's chromium with a +2 charge. Here's chromium, so it's going to fill the 1s, 2s, 2p, 3s, 3p, 4s, and begin filling the 3d orbital. Our particular chromium has a charge of +2, meaning it actually has the electron configuration of titanium. Just like before, I'm going to use a noble gas to make it a little bit shorter. Specifically, I'll use argon as the previous noble gas, and then add on some 4s and 2 3d electrons. So chromium with a +2 charge would look like argon, with the 4s electrons, and then 5 suborbitals for the 3d, only 2 of which have electrons, and again, make sure those electrons are spinning the same way. Tin with a +4 charge will follow the same principle. Here's tin. +4 means it's lost 4 electrons, giving it the electron configuration of palladium. Palladium, just like before, will look like krypton plus some additional electrons. So here's tin. It'll look like krypton plus the 5s and some electrons in that 4d. Specifically, tin will be left with 8 electrons in the 4d. 1, 2, 3, 4, 5, 6, 7, 8. We got that from 1, 2, 3, 4, 5, 6, 7, 8 from that tin +4. Finally, I want to know the arrow notation for uranium. Here's uranium on the periodic table. Recall that this actinide series really fits in right here. So I'll use my previous noble gas, that's radon, add in some 7s electrons, and then some 5f. Remember, the f orbital is actually 2 levels behind the s and the p. So uranium will look like radon, plus 2 electrons in the 7s. Here's the 5f. Uranium will put 4 electrons in that 5f.